So for part 2, U substitution, we're going to be integrating and looking at some trig examples. Okay. What is the antiderivative for sine 3x dx? Well, if it was just sine x dx, then the antiderivative would be negative cosine x. But this is more complicated. It's a composite function requiring U substitution. Notice we don't have any power functions going on. So where do we begin then to look to figure out what U should represent? Well, look for an outside function. The outside function is sine. It's a trig function. The inside function is 3x. So that tells us kind of how to start. U equals 3x. Let's find the derivative. Well, that's just 3. And we need a differential on this side of the equation. All right, looking over here to convert to a U integral. Okay. If I want the outside function to be sine, I know how to integrate sine, so I'm going to leave that alone. 3x is U. Now right here, dx, we have a 3dx, so let's bring in a 3, and then we're going to pull out a 1/3. Alright, so it looks like everything's good to go. I can turn over, convert to a U integral. So 1/3 times the integral. Keep sine, because that's now your outside function. 3x is U. 3dx becomes our du. So just looking at what we have, if this was sine x dx, then we know the antiderivative is negative cosine. U is just a dummy variable. It very well could have been x. We just decided to use U. We're ready for integration. 1/3. The antiderivative for sine. Okay, remember, sine's derivative is cosine, but what do I differentiate to get sine? Well, if I differentiated just cosine, I'm going to get negative sine, but I don't have negative sine. So that must mean that I have to differentiate negative cosine U to get a positive sine U. A little bit of cleanup. I'll pull the negative 1/3 out front. Keep the trig function, which was my outside function here, and replace the U with 3x. Check your work by differentiating, and you'll see through the process of using the chain rule that you do end up with what you started with. For example 2, it's a little bit different. We have two terms. We've been dealing with just one term in the integrand. Now notice that terms are what you add or subtract. I have a 5 term, and I also have a secant squared x divided by 4 term. It might be best for us to separate. We do have a property of integrals that allows us to do that. So I think I'm going to go ahead and separate and say that I really have two different integrals. And that's just because the integration technique that we use is going to be different for each of these terms. So it might be better. So this is one thing that you can do. If you feel like you're adding and subtracting and they're quite different, the terms are, and what they would need to integrate, then it might be best for you to separate and give each an integral with the differential dx. So that's all I did. All right, this is easy enough to see that this antiderivative is going to be 5x. It's this one that's a little more complicated. Okay, so I'm going to come over here and I'm going to go ahead and integrate here and say I have 5x minus the integral secant squared x divided by 4, or 1/4 x dx. So now I can really focus my attention on that more difficult term up here. I do see a power, but I see a trig function. So we really need to have a good handle on all our trig derivatives to be able to identify secant squared as the derivative of tangent. So it appears to me that the outside function is a trig function, not a power function, and if I integrated secant squared, I'd go back to tangent. Okay, well, this is composite. It's x over 4, not just x. So I'm going to come over here and I'm going to think that U is going to be my inside function on my outside trig function. So if U is 1/4 x, then du is going to be the derivative here. It's just going to be 1/4, and then of course I have dx. Alright, so bringing this part of the problem down. Okay, I might want to do a little work here actually before I bring this down. Let's think about what I have. Secant squared x is actually going to go back to tangent, so that's taken care of. The x to the fourth is okay. Here, that's going to be a u, so we'll have secant squared u. This is where we need to kind of do a little bit of work on. If I have brought in a 1/4, if I can bring in a 1/4 here, a fraction here, then I would need to pull out its reciprocal. But you notice that we're not going to go all the way over here to 5x. 5x is done. I'm going to pull out a 4, and I'm actually going to put the 4 in front of just this integrand. Okay, now down here I have the 4 in front of the integral symbol. I'm going to convert to a u integral. Secant squared, this will be u, and then all of this will be replaced with du. So that as we look at this integral right here, we see that secant squared u du is the derivative of tangent. So it looks like we're about finished. 5x minus 4. Okay, and then right here, that just goes back to tangent u. If you want to put u and then in the next step replace u with 1/4 x, that's fine. But it's going to be tangent of u, which is x over 4, and then we have the plus c, the constant of integration. Check your work by differentiating. This becomes 5. Yep, that's what was there. Minus 4 times the derivative here would be secant squared times the derivative of 1/4, which would 1/4 x, which would be 1/4, which would cancel with this 4. So by checking by differentiating, you should end up with the integrand that you started with here. All right, let's look at example 3. Notice that I don't have a sum or difference of terms. I have one term made up of a bunch of factors. So it doesn't look like I need to separate and create individual integrals. All right. Yeah, I do see a power, but that power function is on 7x squared, which happens to be the inside function to cosine. All right, so you might want to think about, in this case, because I have a trig problem, okay, kind of start there and identify this as the inside function. Is the derivative of this quadratic present here as a linear factor? And it is. Okay, so let's let u be 7x squared. du is 14x dx. Let me rearrange this. All right, let's think of the adjustment that needs to be made with the constant multiplier. This integral will become cosine of u, which we can integrate cosine of u back to sine, but we need this to be a 14, so let's multiply by 7. 7 times 2 is 14. And if I bring in a 7 multiplier, I have to bring out a 1/7. So we have cosine of u. All of this will be replaced with du. Easy enough. Look how uncomplicated this integrand is. Okay, so the outside function here is a trig function, cosine, and we know that goes back to sine. So 1/7 times the sine of u. And here you could put u in the next step, replace u, but if you're comfortable combining the two skills here together, that's fine. So sine of 7x squared. You can check your work by differentiating. If you think about it, this just being a constant multiplier, the derivative of sine goes to cosine. We would leave 7x squared alone, which is present here, times the derivative of 7x squared, which is 14x. We have the x. The 14 would be multiplied by the 1/7, which produces the 2. So if you're ever unsure, again, you can always check by differentiating.
Oh, my phone's closed.
For example 4, you might want to pause the video, attempt it on your own, and then come back and see how you did. All right, studying what we have here, it appears, because I see a trig function, one of the first things I think about, okay, is the trig function the outside function? So that would mean let's proceed forward, and if the trig function is the outside function, 7x plus 5 would be the inside function. And is the derivative of 7x plus 5 present as another factor? And it is, because the derivative of 7x plus 5 is just 7, And even though 7's not here, I could bring it in. So I have an idea of how to proceed. U is going to represent the inside function. The derivative here would be 7 with dx. Looking over here, okay, cosine's good to go. This would be u. And then for dx, I need to bring in a 7, which requires me to pull out a 1/7. So rewriting, 1/7 integral cosine u. 7 dx gets replaced with du. Easy enough. It's an uncomplicated integral. Antiderivative for cosine of u goes back to sine of u, or in this case quantity 7x plus 5, and don't forget your constant of integration. And again, you can check your work by differentiating. All right, taking a look at example 5, we can see that this integrand is pretty complicated. We have a product, a lot of trig functions. Again, if I see a trig function, I'm going to begin to think about in my memory what are the derivatives of the 6 trig functions. So when I see cosecant times cotangent, both with x squared as the argument, or the inside function if you will, when I see the product cosecant cotangent, I'm thinking that this is the derivative of cosecant. Of course, the derivative of cosecant is negative cosecant cotangent, and we can simply bring in a negative, so it's okay that that there's an absence of a negative sign. All right, so that's the first thing you might want to think about is your trig derivatives. You might be able to go somewhere with that, otherwise you have to come up with a plan B. But for this particular problem, we can see that cosecant x squared times cotangent x squared is going to be the derivative of a negative cosecant x squared. All right, so the outside function in this case is really a trig function. So the inside function, which is what we want to let u be, is x squared. And it makes sense if you think about it, because the derivative of x squared is a linear function, 2x, of course with the dx, and x is an additional factor here. It's also what we're multiplying by. All right, if we think about taking x and putting it behind here next to the differential dx, we can see that we have x dx, but we need 2 of them. So instead of rewriting and taking the time to rewrite and rearrange, I'm just going to say at this point, hopefully we see that we would move x dx here, and I need to bring in a 2, 2x dx that is, so I would pull out a 1/2 to counter that 2 I brought in. All right, so let's see what happens here when we rewrite. So we have 1/2 integral. Okay, so we have cosecant, cotangent, x squared. So I'm going to simplify by saying cosecant u times cotangent u. That takes care of this. And then the 2x dx will all be replaced with du. So kind of looking at this integrand right here, you guys can now see it maybe a little bit more clearly that cosecant times cotangent is the derivative of, it would be negative cosecant. Okay, so now we can proceed with integration. So 1/2. The antiderivative for cosecant cotangent would have to be negative cosecant u. And if you wanted to go ahead and combine replacing u with x squared, that'd be fine. So you could check your work by differentiating. The derivative of cosecant x squared would be cosecant x squared cotangent x squared negative, but this negative makes it positive. Derivative of the inside function using the power rule would be 2x. X is present here, and the 2 would cancel with the 1/2, which would take care of not having any multipliers here. So I encourage you guys to, anytime you get a chance, check your work by differentiating. So this last example is a little bit more interesting. It's going to provide some challenges for us, so let's kind of see what happens with it. It's pretty complicated looking. I encourage you, okay, the first step is to rewrite negative or exponents that are in the denominator as negative exponents. So that would be the first thing that I would try. So rewriting this, I'm going to pull up, okay, this expression and make it cosine 2x, and that's all going to be raised to the negative 2 power. That would be the first thing that I would try. We're going to see here shortly that it's we're going to kind of hit a roadblock, and we're going to have to come up with another idea. Anyway, if the squared's down the denominator, it comes up as a -2, and remember that it is on the trig function, so that's why it becomes the outside exponent here. All right, so for this particular problem, we need to identify the inside function. Well, when I see a power, I do think of, and the whole expression is to a power, I think of the outside function being -2. So if the outside function is -2, then that means that all of this cosine 2x has to be the inside function. So let's just kind of think about that and put it before our eyes here. If u is this inside function, so that I could integrate u to the -2, then the derivative of cosine 2x has to be a factor, okay, on the integrand. Well, the derivative here, it's pretty complicated. It's the chain rule. It would be negative sine, leave 2x alone, times the derivative of 2x, or times 2, which I would multiply in front here, and then I'd put the dx on here at the end. Well, you can clearly see that we don't have another trig function. We don't have anything but cosine. So we can't proceed this way. Okay, some students often say, well, let u be 2x. Well, we could try that. If u is 2x, then du would be 2dx. And then they would think, well, let's bring the 2 in with the 1/2 out here. Well, let's see what happens if we do that and we try and integrate. Let's put the 2 here and the 1/2 here. Okay, if I were trying to proceed here and integrate, I'm going to have 1/2 integral. I would have cosine cosine u du, but this is still to the -2 power. And what we're looking for is we're looking for this integrand with the u integral to be something that's basic, a basic integration rule. Well, I mean, it either has to all be x or u, if you will, to the -2, okay, or it just simply has to be cosine u. I can't have a combination here. I can't proceed this way. All right, so that takes us back to the original problem, and we have to come up with something else in our brain. Well, think about rewriting this using some trig properties we learned in the past. Okay, we know that, just kind of over here, 1 over cosine x is equal to secant x. So 1 over cosine squared x must equal secant squared x. So what I could do is I could take this integrand and rewrite it as secant squared, using reciprocal properties, okay, secant squared of 2x dx. All right, so let's study our new integral. Well, think of trig in calculus. The derivative of tangent is secant squared. So perhaps secant squared is the outside function. Perhaps the trig function is the outside function. So secant squared is the derivative of tangent. That would have me let u be 2x. If u is 2x, then the derivative of 2x is 2, which is just a constant, which I can handle. So I think that's how I'm going to proceed. I'm going to come down here for myself and rewrite this. Give myself a little more space. Come over here. Let's let u be 2x. du is 2dx. All right, coming back over here. Okay, I know that secant squared's okay. If it's the outside function, I'm good. This is u, so secant squared u. Now I need to bring in a 2 and pull out a 1/2. So we have 1/2 integral secant squared u, and then this is du. Okay, we've uncomplicated it. The secant squared u goes back to tangent. So 1/2 tangent u plus c. Well, u is 2x, and then we have plus c. You can check your work by differentiating. The derivative of tangent is secant squared, leave 2x alone, times 2, the inside function's derivative, and that would cancel with the 1/2. I could then further take secant squared and rewrite it as a 1 over cosine squared 2x. So that was a little interesting because right here what we needed to do was we needed to think of not calculus first but pre-cal, and how can I rewrite that. So if you see 1 over cosine, you might want to be thinking about secant, and especially if you see 1 over cosine squared, secant squared is convenient because that is the derivative of tangent. It's trial and error. Sometimes you hit roadblocks, but try and have a plan B. Think about algebra, rewriting things using algebra, okay, to help you with the calculus. Think about trig, pre-cal, rewriting integrands using your background there that can help you with the calculus.